Good. Okay, once again, good afternoon. Today we will look at I would say, different kind of use of pointers, that is during for dynamic memory allocation. Okay, just maybe if I want to motivate why dynamic memory allocation is necessary, let us think of a static array. It's an int array, a of size, max size. Okay, so the point is that I may have max size equal to 1000. Okay, this is possible, right? And if so, this array A, when declared, is capable of storing 1000 int variables. Okay, so A can store just 100 int variables. But then I ask the user, how many integers do you want to store? And the user may say, scan something like n, and the user says n equal to 20. Okay. So then you are actually using a 0 through 19. Okay. So that implies that 980 entries in A are wasted. Agree, right? The user just wants a 20 sized array, but some other user may ask for 100 sized arrays. So as a safe upper limit, we have taken max size equal to 1000. And if somebody says 20, so a very large fraction of this storage, that is 980 integer entries, they are essentially wasted. Okay. With static arrays, this waste perhaps cannot be avoided. Okay. On the other hand, if some user says, I want n to be 2000, okay, then since you have prepared for an array of size only 1000, you cannot store 2000 integers in this. So in this case, you have to say goodbye to the user, to the effect that I have an array capable of storing at most 1000 integers, but you are asking for an array of size 2000, so I cannot do it. So better luck next time, or something like that. Okay. You should not allow the user to store 2000 integers in an array where the allocation size is only 1000, because if you do so, you essentially go outside the legal boundary of A, and you create havoc. Okay, potential havocs. So all these problems can be handled using dynamic memory. So the user enters, user gives n, and then you allocate an array to store exactly n elements. No more, no less. So this is the most effective use of space, right? The user wants n equal to 20, then you prepare an array of size 20. The user says 2000, you prepare an array of size 2000. Exactly as the user wants, you just dynamically allocate an array. So an array of such dynamic size is definitely going to be useful. It first prevents waste of space, as in this case, or denial of service, as in this case. Okay. So the question is how? Okay, so I now supply you with the general syntax for asking for dynamic memory. So you have a pointer p pointing to some type. Type can be something like int, char, double, or even bigger things like struct std. Blah, blah, blah. Okay. And then the user specifies n, size of size of the dynamic array. Size, of course, size in number of elements, not byte size. Then what you will do, this is a generic call, assign to P a dynamic array of type star, then the relevant call is malloc, which is an abbreviation of memory allocate memory. And here I have to say size not in number of elements, but size in bytes. So this is the generic call. So you make a distinction between this. N is the size of the array in the number of elements. Each element is of type. But in this malloc call, you can request for the number of bytes, not number of elements. For example, if we have n elements of type, then you should write n star size of type. Okay, so malloc type star. So this is the generic allocate memory call. The function name is malloc. It takes a single argument, the amount of raw memory you are asking for. That should be the amount of memory you request in bytes, not in the number of elements depending upon type. Okay, so size in bytes. This is something I highlight. This is not number of elements, number of bytes. So if your type is type, then it will be n times size of type. Okay. Now this malloc returns what is called a void pointer. Okay. And that void pointer can be typecasted to pointers of any other type. In this case, it is type, so I have typecasted it to type star. In my machine, in my compiler, this typecasting is not exactly very necessary. because the compiler can automatically handle this typecasting from void star to whatever the type of P is. But maybe it's a good practice to write this in order to keep all the compilers happy. Okay. So if this memory allocation request is successful, then the required, whatever the required size in bytes, this much memory is given to your program for your own use, and the start address of that memory location, whatever is allocated, that is an address. That address will be returned to P. Okay, so let me write down. So malloc successful. Then we will have 1, 2, 3 up to n cells of type. This will be created, and the start address is returned to P. After this, you can use this P like an array. Okay, as we have mentioned, P0, P1, P2, up to Pn minus 1. And you know that there are other alternate notations like star P plus 1, star P plus 2, and so on, star P plus n minus 1. Okay, so this now looks like an ordinary array. Only thing is that this is not statically allocated, but you allocated memory for this during runtime by making a call to malloc. Okay. And what happens if malloc is unsuccessful, if it fails? Then there is a particular type of pointer called the null pointer. So P becomes the so-called null pointer. So this capital N, U, capital L, this is actually a reserved word. This stands for the null pointer. Essentially, it is the address 0, and actually nothing resides in address 0. So it is essentially, it returns a pointer to nowhere. And if you try to follow that null pointer, then you are in danger. Okay. So in general, I would say malloc requests do not fail as long as there is sufficient memory. So you want something like 100 bytes, 1 million bytes. There's still not too much memory, because nowadays we have memories of the order of GBs, 4 GB at least, even in your cell phone. Okay. But if for some reason memory is full, or you have asked for a tremendous amount of memory, then the malloc may fail, and then the null pointer is returned. NULL, all in uppercase. Okay. So if you have a doubt whether I would say malloc succeeded or not, after making this malloc request, you may check if it is null. It's a good practice. In general, it is not needed if you want a small amount of memory. You know that you asked for some memory which the system could not provide, and therefore you cannot proceed because the rest of the program is based upon the assumption that P has something, P is pointing to some valid memory. So it's graceful termination. If malloc is unsuccessful, null is returned, you check it, and then you do exit with some error status like 1. Okay. So this is the basic way of handling dynamic memory. And once you are successful in having an array against your pointer P, you can use it like other arrays, static arrays. Only thing is that the size is not predefined. Instead, it is based upon whatever n you provide during the runtime. Okay, so that's the basic syntax.
Sir, so excuse me, sir.
Yeah.
So after allocating the memory, so the means random pointer means non-static pointer is converting to static pointer. So is it so?
No. Maybe you are asking things in advance. Uh, shall I answer now or little later? Uh, it's not a static thing actually. You can again allocate memory to P using another malloc call. But then if you do not keep track of this address, this memory is essentially, it is still under your control. But if you do not hold this address somewhere, this machine is essentially what is called a garbage. It is allocated to your process, to your program, but you have lost track of it. But anyway, let's not worry too much about this. Okay. As I mentioned, P is not a static array. So P can be a valid L value in any assignment. Even after making one malloc call, P can be L value in future assignments. Okay, but let's not worry too much about this. I would say nitty-gritties about uh, pointers. First, let me understand that you understood the syntax, how you ask for raw memory, how you get it, and after that, what can you do with it? Is this much clear?
Sir,
Yeah, tell.
sir, what is void pointer? I didn't get that.
What did you not get?
What is void pointer? What
Void
does
pointer.
it mean?
Void pointer you do not need to worry too much about. Let me show you one thing. Manual of malloc. Okay, if you have a Linux machine, then of course you can always run it's a manual malloc. Okay, so you see that you are specifying size. Okay, size underscore t as actually something, and it returns void pointer. Okay, now void pointer is a generic pointer type in C, and you see that this is defined in stdlib.h. Okay, there are three other things: free, chunk alloc, and realloc. If needed, you can look at this. I will tell about free little later, but this chunk allocation and reallocation, this you look at manuals or books or notes or online resources, wherever you find it. For us, this malloc and free are sufficient. Okay. So void pointer is a generic pointer type in C. It can be typecasted to any other pointer. Okay. Apart from this, you do not need to know anything. Void pointer plus plus means it will stay there. I think the size of void pointer should be 0, whatever it is pointing to. But anyway,
So we can
this
convert the type of any pointer to any other type to which it can point. Like
you
if
can
it
do
was
it. You
int
can
pointer.
always do it. Yeah, you can always do it. But in C, this void pointer is a kind of generic pointer, and almost silently, it can be converted to pointers of other types. And that's why I mentioned it is returning void pointer. You are explicitly converting it to a type pointer, but this portion is perhaps not necessary. Even if you do not write this, many compilers will silently convert that void pointer to this whatever the type of P is. I am just using this type pointer here in order to keep everything happy, everybody happy. Okay.
So that type start thing that you've written in brackets is just like typecasting that malloc thing, right?
Yes, yes. From void pointer to this, in
So,
general, this is
so then
automatically done.
why did you write like returns void pointer in the second line when you are already typecasting it explicitly?
No. You see, I show you this. It is returning void pointer. I am typecasting it to this type pointer. Okay. It will always return void pointer. But anyway, you don't need to worry too much about this.
But you just said that bracket inside the bracket you wrote type star. That means that you are typecasting it from malloc void pointer to that particular type
Whatever
pointer.
it is returning, you are typecasting it to the exact type of P, which is type star.
So just a blank statement of malloc size in bytes will return a void pointer.
Yeah, that will also work. In general, that will work, but just in case in some compilers you have a problem, the conversion of void pointer to type pointer is not automatic. The compiler will raise some error
That
message.
is why the type star you are explicitly
It's
typecasting.
in general redundant. I
Okay,
understand.
understood, sir.
Okay.
So, and one more question, sir. The malloc actually like allocates and reserves the memory which is given in bytes on adjacent to this pointer p where it is defined, and
Yeah.
it does that dynamically. So that is the advantage of it over static pointers like arrays.
Yes. During runtime, you can actually specify the size. Whatever you want, you just want that much. And as I mentioned, there is something called realloc. If you reallocate, then you can actually change this size. But anyway, let's not worry too much about realloc.
Okay, sir.
Sir,
Got it.
Okay.
sir, in
So
the beginning, you said that one of the advantages of malloc is that if you need to increase number of elements, you can do that. But then, what if you need to increase more than n? You cannot do that, right?
no. Maybe for the moment you are working with 100 student records. Okay. Then ERT says, okay, we have got 10 new students. You should handle those. Then you have to, an array of size 110. So you can use the same pointer, but if you reallocate it, then instead of the size 100 times type of struct stud, you can simply say 110 times size of struct stud. Okay, the old thing will stay. 10 more cells, each holding something like struct structure, will be created. But anyway, let's not worry too much about realloc. If you are interested, you can look at the man pages, you can read books, online resources and other things. Let us only be happy to be completely or reasonably exposed to this malloc command, and I will later tell you what is free.
Sir, so then, other than realloc, what is the difference between normal array and malloc?
Normal array is static, right?
Okay, got it.
You cannot change anything. It cannot be in the left of an to the left of an assignment statement. But this is a pointer. You can do it. You can make two successive malloc calls and assign the same thing to P. This is always allowed. This is just a dynamic. This is just a pointer, nothing more than that. And you are simply saying that instead of earlier, what did you do? Recall. Ouch. Ayo. Okay. Earlier, what did you do? Yesterday, we have seen something like that. Int a 10 star p. And we said p equal to a. So this is a valid assignment. You are essentially allocating to p the address where this array begins. You can also, if you say p equal to int star malloc 20 star size of int, Then you can say this after this or this after this. This is always fine. So this will be, this is now A is a static array. A static array. And this malloc call creates a dynamic array and returns the starting address to P. In fact, the difference between this is that these two types of arrays come from two different parts of the memory, but you do not need to worry about this too much. Static arrays are allocated from the stack part of the memory, whereas dynamic arrays are allocated from the heap part of the memory. Okay. So they are both accessing the main memory, but static arrays are essentially organized in the stack part. Dynamic arrays are essentially organized in the heap part of the memory. But what is the difference between the two? You do not need to worry.
Excuse me, sir.
Yeah.
Sir, what does it mean, a stack part and a heap part?
You don't need to understand. Just keep this word in your mind. Okay, I cannot explain this. Because this requires something like operating systems and all that stuff. This is beyond the scope of this.
So suppose if I store some values in the static array, like suppose if I store some values there, and then I allocate the memory dynamically using this pointer, then can I access those values, or do I have to initialize this?
No. First of all, let me be very, very precise. You cannot dynamically allocate A. Because it is a static array. Because if you want to do, you have to write A equal to something. And if it is a static array, A cannot be on the left side of any assignment operation. Right? Yes or no?
Yes, sir. So actually my question was different. Like, suppose if I have already stored some values like 2, 3, 4, and so on in the static array, and now if I did this operation with the pointer like star p and then p equal to a, and then I dynamically allocate some memory, some more memory to it, then will I be able to access the previous elements which were already there?
Yeah. That is what I am saying. If you say p equal to a, okay, then p will point to this, and then you may say p2 equal to 5, p99 equal to whatever, blah blah blah. Okay. Then you say p equal to, okay. Then you say p equal to this. Then a dynamic array will be created, and p will point to this. Reference to a is lost. It's a pointer. Whatever address you store there, it will store that thing. If I say,
means we cannot, we have to
if on a third line you say int star, again you say malloc 5 star size of int. Okay, so this is statement 1, this is statement 2, this is statement 3. Then what will happen? The runtime system will try to allocate memory of capable of storing 5 times 4, 20 bytes, and whatever it's another array created, and that pointer will be returned to this p. So whatever old value this p was containing, that is lost. It's like you say int n equal to 5 and then you say n equal to 10. 5 is lost. It's something very much like that.
So we have to reinitialize this new array with these old values if we need them. Yeah.
Reinitialize means? Yeah, it's just a new memory. This is just
was lost.
memory.
So
this is a new memory. Once again, you have to reinitialize it and work on it. But more importantly, whenever this allocation of P changes from this array to a new array, this array still resides in your memory. Only thing is that you have lost
the reference is lost.
You have lost this address. So this is what is called a garbage. You have lost track of this memory because you have reallocated memory, or not, it's not reallocated, I would say in the realloc sense. yeah, again allocated a memory. You have lost track of this, but this is not returned to your system. So this is essentially waste.
So
Okay, sir.
we can delete that after we lost its reference.
Uh-huh.
We can't delete that amount of memory
That is what is
after
called
we lost
free.
its
That is what is done by free. I will come to that later. Okay. So it's a good practice. You free that memory and then once again reallocate malloc. Okay. So that is what is done by free. I will come to that later. Let's first allocate and then we will see free. Okay. So yeah, unless you free explicitly a dynamically allocated memory, it will not be returned to the heap. You cannot reuse it. Okay, so that's important. But anyway, we will study that when we talk about heap. Maybe I will do one thing. I will just give you an example of dynamic allocation. Of course, whatever I am whatever I have told, this is nothing but that. But anyway, just have a pictorial description. Okay, so maybe this is inside main. You declare an int variable I, a sum to be 0, 2 pointers A and P. Then let's see. So that means this is a variable I, a sum that is initialized to 0. A and P are 2 pointers. Sometimes I show pointers like this. Okay. And that means this will point to something. And if it is the null pointers, it's a standard practice to ground this. Okay, so this is a null pointer and this is pointing somewhere. This is the pictorial description. And here I do not know because I have not initialized A and P, and therefore I do not know whether it is pointing to anywhere or it is simply grounded. Okay, the null pointer. So I just keep it like this. Okay. Later, you see that I am asking for a memory capable of storing 5 integers. And this is an int pointer. So I am, for the sake of, I would say, safety, I am converting that void pointer to int pointer and assign that to A. Okay, so let's see what happens. Then an array of 5 int elements is created, and the address of the 0th element in that dynamic array will be returned to A. So at this point, after this malloc, I assume that it is successful. A now points to the beginning location of this array, dynamic array. Okay, this is the effect of malloc. Then I can use this A like other arrays, A0, A1, A2, A3, A4. I can store these values 11, 13, 17, 19, 23. It works like this. A0 is 11, A1 is 13, A2 is 17, A3 is assigned 19, A4 is assigned 23. Okay. This is functionally as if you are dealing with an array, only the size was something which you just specified during runtime. Okay. Here, of course, it is a constant, but it can be coming from a variable, which itself is coming from user input or from the result of some computation. Okay. Now I say P equal to A. So P is an address, A is an address. The address of A you explicitly got by the malloc call, and I can say P equal to A. Okay, these are all int pointers, so I can say P equal to A. So P will now also point to this. Okay, same address as A, P equal to A. Happy or not? Then what I will do in the sum variable, I will compute the sum of this plus this plus this plus this plus this. And I know there are 5 elements of them, so I will run a loop for I equal to 0, I less than 5 plus plus I. I will simply add star p, whatever p is pointing to sum, and increment p. Okay, let's see what happens. And sum is initialized to 0. Okay, so I equal to 0, star p is 11. So 11 will be added to sum. Sum becomes 11. P is incremented by 1. So P now points to the second location or the index 1. Okay. And once again you increment I and go to the top of the loop. So I is 1. This is still less than 5. So you add to sum, which is already 11, the new value that P is pointing to. Start P is 13. So 13 plus 11, it will now become 24. Okay. It becomes 24. Again, you make P plus plus, P will point to the next location. P comes here. Go to the top of the loop with I equal to 2. This is still smaller than 5. Go ahead. Add 17 to that earlier sum. It becomes 41. Plus plus P. P will come there. Next element. And again, you go to the top of the loop with I equal to 3. Not done. When you add 19 to it, it will now become 60. 60. Increment P. Okay. I becomes 4 and you go to the top of the loop. 4 is still less than 5. So there is another element to add. 23. So add it to this. It will now become 83. 83 plus plus P. But of course, by looking at this, you cannot simply say whether the array is ended or not, because integer arrays are in general, unless you follow a specific standard, they are not by default null terminated. Okay, but you know that you are going to sum add 5 elements, so this actually takes care of breaking this loop. So after 4, I becomes 5, 5 less than 5, this is not satisfied. So the loop breaks, okay, and the desired sum is stored as 83. Okay, tell me if this animation and the implications are clear or not.
Yes, sir.
Okay, good.
Yes, sir.
Okay, this is how malloc works. You are asking for these many things, you are getting it, and then use it like other arrays. That's the basic, I would say, the basic point, basic element of this call. I mean, basic element of this part of teaching. You get an array of size 5 in variables, and then use it like an ordinary array. And whatever you do with arrays and pointers, you can do. Okay.
Sir,
Yeah.
sir, is there any other method of initializing this array, or we have to initialize it only element by element?
Initializing is not automatic using malloc, but as we have seen, there is a call called chunk alloc. This actually initializes to 0. Okay, but its syntax is slightly different. Okay, so if you are interested with this chunk alloc, oh, this is no longer active. Yeah, so calloc I should find here. Calloc function allocates memory, blah blah blah, and the memory is set to 0. Okay, but malloc does not make any attempt to initialize. It essentially contains junk. Okay, but chunk alloc, calloc initializes it to 0. Okay, but if you want to learn how to use calloc, so use either this man pages or other things. Okay, so you have to do this initialization yourself. Yeah.
Sir, my question was that, like in static arrays, we can write curly braces and through comma separated integers, we can initialize the integer array.
This will not work
So,
here. This will not work.
Okay, okay, sir. Okay.
And this I may have to, I would say, I do not think this will work. We may try, but maybe. Uh,
A is essentially a pointer, so will it work like with that syntax
yes,
work
yes,
with?
yes. You are essentially allocating a pointer value. It's not an array you are assigning to A. Yeah. So that kind of initialization will not work. Yes, yes. So A gets an address. Okay. This array is created as an what is that called, as a uh, I mean, as a side effect. Whatever is assigned to A is the address, an address. Okay. This amount of memory that you get, this is just a side effect. This is a kind of byproduct. Okay. So you are given some raw memory, and then whatever you want to do there, and you are given the address at the beginning, then whatever you want to do there, do it.
Okay,
Yeah,
sir. Yes,
like
sir. Okay.
Excuse me, sir. Hello, sir.
yeah.
Sir, in this case, if we do this size of function on A, we will get 8, right?
What is A?
And sir, the
You
A is
tell me.
pointer.
A is a
A
pointer.
is
So whatever
pointer.
the size of pointer, you will get it.
Yes, sir. It won't return the size of the array.
A is a
Like
pointer.
in the
A is not an
yes,
array.
sir. Not
A
an
is a
array.
pointer.
Yes.
Okay, so that's the difference between static and dynamic arrays.
Yes. Got it.
Okay, yeah. This size you can never tell how much you allocate it. Yeah.
I once tried to like use the size of function with a pointer. No matter what type it was that the pointer was pointing to, it always returned 4, like 4 by 4, whatever type the pointer was of.
No, this question is not clear to me.
Like suppose int star p I had declared and double star p2 I had declared. I tried to use the size of function with these two, and but it still returned like 4 only for both these pointers.
No, if I understand your query correctly, I can anyway say A equal to instead malloc 7. Just give me 7 bits, 7 bytes. I can say that.
Yes, I actually was talking about the size of pointers variables as a whole.
Size of
Like
pointer
what is the
variables. Yeah,
size?
whether it's double pointer or
Sir,
struct pointer or int pointer or char pointer, it doesn't matter. Pointer is a pointer, it's just an address.
Yes, sir, and it always returned 4, no
They
matter
always
what
the same
the type
size.
was.
And that size depends upon your system. It may be 32 bits, I mean 4 bytes, 8 bytes. I usually do not expect 12 bytes or something, more than 8 bytes. That will be huge amount of memory. So in modern machines, you typically expect 8. Size of pointers is 8. And that is irrespective of whatever it is pointing to. Even a white pointer has size 8. Okay.
Yes, sir, got it.
Okay. The type of the pointer is needed when I say a plus 1, a plus 2, a plus 3. So plus 1 means how many bytes you want to skip. And it is only there where the type is important. Right? Or you say A0, A1, A2 like this.
Yes, sir.
How much I will skip to go to the element at index 1, element at index 2, element at that actually requires the type, whether it's an int pointer, it's a char pointer, double pointer, struct std pointer. Okay. They are actually this type of the pointer matters. Otherwise, all pointers are
Yes,
of the
sir.
same side in the same system. Okay. Yeah.
Yes, sir.
Sir,
Yeah. Tell.
pointers can be used only for one-dimensional arrays, right? Otherwise, we have to use struct.
Now, what do you want? You want
Answer.
two-dimensional pointers.
Yes, sir, dynamically. We can allocate.
We'll do. Let me first get convinced that you understood the one-dimensional array allocation. Then we will do. In the next class, we will do 2D kind of 2D array pointers. It's a much more complicated thing than this. We will look at it. Today I do not have enough time. Or let's see. Today thing we will study in
Sir,
detail in next class.
I initialize the array without manually initializing it somehow.
No, what do you say?
Sir, you are saying that have to like manually initialize it. So
This is manual initialization, right?
yes. Sir, nothing, sir.
Okay, it's not using a single thing like 11, 13, 17, 19, 23 within curly brackets, comma separatedly. This will not work because A is a pointer. Okay, yeah. Okay, so if this much is done, what do I want to illustrate? Maybe I write a small code to show you how malloc works. Maybe I just mention this. Two-dimensional thing I cannot start because it's already 4. Free pointer. This is just the syntax. So you say A equal to type star, maybe int star, blah, 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 malloc, whatever. And then you no longer require this memory, you simply say free A. Okay, that's the syntax. So return the allocated memory to the system so that a future malloc request can again get the same memory. Okay, but the important thing about this is that after this, whatever address A is storing, so for example, A does not, by this call, become a null pointer. A is pointing somewhere, some valid address. That address will continue to say. You just say that the amount of memory that you obtained using this malloc call, you just simply return that to the system memory. Okay. Nothing else happens to A. Only thing is now A is pointing to some earlier allocated memory location. And this may go to another, I would say, chunk of memory called by another invocation of malloc and so on. Something was written is that I was concerned of the fact that no matter what the data type of pointer I am declared it's returning the same size in bytes. Yes. Basically the pointer stores the address, size of parameters to the pointer variable selected in the same number. Okay, anyway. Okay.
Sir,
Yeah.
free will clear all allocated memory. Free will clear all allocated memory. Suppose 20 bytes. Free A, sir.
What?
Free A will clear all of the allocated memory.
Free will not allocate everything. Only the memory allocated to A. If you have other dynamically allocated arrays like B, C, D, those will not be free. One by one, you have to free everything. Okay. Yeah. So it's not very, I would say.
Sir, I have a question.
Yeah, tell.
Sir, if the value of A does not change, like the memory will still be accessible, right?
Memory will be accessible. Yeah.
So, like, how will it be freed? I don't understand what do we mean by freeing the memory then?
Free does not mean, look, so you define something like this, int star A. Okay, you didn't initialize A to anything. So it is holding some garbage value? Yes or no?
Yes, sir. Yes,
Okay.
yes.
Still it is a garbage address. So after free, just consider it as a garbage address.
Achha, like different applications or other programs can use this memory, but
Exactly.
from this program we can still access it.
You can still access it, but it's most likely garbage.
Achha, but we can't like we won't be able to assign anything to it, right? Once we free it.
You can do it as long as there is no, segmentation violation, segmentation fault kind of thing. You can assign
We
things.
can assign also. Okay.
Yeah, it's an address, right?
Yeah. That's
It's something.
no like.
It's a think of something like this. You own a house, okay? So you can go and paint the wall there, okay? Then suddenly you sell this house to somebody else, a third party. You can still go there and try to paint there. Nothing prevents you from doing it, right? So, but if the new owner actually kicks you out, there is a problem. It's exactly the same thing here. It's your house, you can go and print it, paint it, okay? But if that memory is allocated to some other thing, then you have some problem. Okay, is it clear?
Yes, sir. Now it's clear.
Yeah, it's something like this.
Hello, sir.
Yeah, tell.
What if we do not execute the free A statement at the end of program? Means that memory will not be reusable. Is it like that?
Well. When eventually your program ends, the system will take stock of whatever memory you actually asked for, and it will return everything to the system. That normally happens in, I would say, responsible operating systems. It usually happens. When you say exit 0 or there is an implicit exit, all the memory that you actually asked for, both in the heap part and the stack part, they are actually returned to the system pool. That is what usually happens. But so long as you are still running the code and you have not explicitly freed the memory associated with A, this will continue to stay. Okay. When the program terminates, this will be automatically returned to the system pool. But if you do not do it, okay, so long as your program is running, this memory is just allocated to your process. So inside a loop, if you make repeated malloc calls, you get more and more and more memory, right? And eventually, even if each allocation size is small, something like 1000 integers, but if you run the loop quite a few times, like million times, eventually you will run out of memory. Okay. So the idea is that if you are no longer using a memory, dynamically allocated memory, free it. Okay, so that's the good programming practice.
So, sir, once we free a particular memory, so that memory address can be once again used even though the code is running. Means in a single run of the code, if we free a memory, then that address can be assigned to something else as well.
You cannot assign. The system is
The
free
system.
to. Yeah, system is free to assign that thing again.
But if
Yes,
we do not do the same, if we do not free, then that will not take
that is
place.
tied up. That is tied up to your program. It cannot be reallocated.
Okay, sir. Thank you.
Okay. So this memory management is different from static things, static arrays. So, for example, if you declare a static array inside a function, and that the function returns, okay, then that static array will automatically vanish. Whereas if you do a malloc inside a function and you come out of the function, that memory will still be attached to your program until you free it explicitly using the free command. Okay.
Okay, sir. Thank you.
Okay. So in fact, this has this implication. Maybe it's not written somewhere, but maybe I erased. Let us think of these two types of structures. One is a static array. Maybe you have a name, roll number, but this roll number is, no, not roll number, let's say CGPA, but this is just float. And you have, what is that called, int. Whereas name is a character array. So this is one kind of struct too. I am not talking about the roll number field. But I can also have something like this. So this is just a character pointer. Then you have a float. You have an int. Okay. This is age. This is CGPA. Now inside a function, you create dynamic memory. But that dynamic memory is not part of this struct. It is external to the struct. Your struct comprises only this thing, int, float, and a pointer. And here it comprises int, float, and a character array. If you have just a pointer, only this pointer remains within the space, whatever you call the struct. You may allocate memory, dynamic memory to this pointer, but that is external to the structure, whereas this is internal to the structure. Okay, that's the difference in having, I would say, this is the static memory inside a structure, whereas this is just a pointer. So only this pointer is the member of this structure. Whatever memory you allocate to it, that is external to the structure. Yeah, this is also an important thing you need to understand. Okay, so yeah, you tell if you have any other questions, because I don't think I can start a new thing now. It's already too
I
late.
could not understand this.
This concept.
Yes, sir. Yes, sir. Sir,
Sir,
should
please
we
give one
allocate
struct
memory in
example.
structure or?
Let me. Okay, if you understood, I think you can leave. Otherwise, I will explain this using writing a small code. Okay. Just let me give it an abstract. Let us define two types of structures. Struct stud char name 100 float CGPA and int h. Struct stud2, maybe stud1, stud2.
So we have to put semicolon like at the end of all.
Yeah, I just missed it. So instead of this static array, I am just now using a pointer. Other things are same. Float CGPA, int h. Okay, semicolon. So what I now say, struct stud1 s1, struct stud2 s2. Okay. Then what I will do, size of S1, size of S2. So this size will be 100 plus 4 plus 4. You expect 108 to be the size of S1 because it is of type struct stud1. Instead of S1, you could also write struct stud1. Okay. This is now just a pointer. So 8 plus 4 plus 4, 16. Let us see whether it gives this same. Struct. $108 and 16. Now let us see. I can say something like this: S2 dot name, which is the pointer. I can simply say char star malloc 100 star size of char. I can do it, right? Now this is a static array containing 100 characters, whereas this is a dynamic array containing 100 characters. And I may write some name there, some here or here. Now, irrespective of how much memory you allocate, you will see that the size of S2 remains the same. 108, 60. 8 plus 4 plus 4. So only this pointer is inside this struct stud2, S2. Whatever memory you allocate to it, it is completely external to this structure. This is what I wanted to say. If you want a bigger size array, go ahead, no problem. This size of S2 will not change. Yeah. So is this clear? What I wanted to mention?
16 why?
Yeah, this is 8, 4, 4. In my machine, pointers are 8 bytes. So 8 plus 4 plus 4, 16. Here it is 100 plus 4 plus 4, 108.
Oh, acha. Okay. Yeah.
Okay. So this array, which is a static array, is inside this struct. Whereas this array, which is a dynamic array, this is outside this struct. The struct only contains a pointer. That's all. Whatever memory you allocate to that dynamically memory you allocate to this pointer, the size of the struct does not change because this array is external to the structure. The structure just contains a pointer. Yes or no?
Yes, sir.
Okay, understood. Good. Okay, so I actually desired to start 2D memory allocation, but anyway, let us do it in the next class. It's a little bit more involved than 1D memory allocation, definitely.
Sir,
Yeah, okay.
how is this beneficial that if we declare a pointer inside a structure, then means in terms of memory, the storage will be more or less the same?
More or less the same, but the point about pointers is that you can allocate memory as and when needed, and the exact amount that you want. That's it. For the moment, it's only this. There are other uses, but one by one, I am just telling you all the uses.
Okay, sir.
Okay. In fact, something we will see in the next week is that I am allowing a pointer to allocate memory to not store just an array, but just one element. Just one element array. So it's not exactly an array, it's a single element. But what is important is that that element itself will contain a pointer of that same type. Okay, so we have a situation like this. Anyway, we'll study. When you study linked list, we have a pointer. We're allocating something. You can store things here, and you get another pointer for free. Again, allocate it. you get a cell like this. Okay. Again, this is just single amount of single one element array. Okay. This way you can chain up or link several data items in the form of a linked list, or you can do something like this, tree structure. Okay. This is where actually pointers are more useful. Or maybe I would say in C, this is the only way of doing it. Creating dynamically linked structures. Or the only obvious way of doing it. Anyway, we will look at it later.
Okay, sir.
Okay. So first of all, understand that pointers do allow you to look at the internal details of the memory. So you can go ahead and look at it. Most programming languages do not allow you to do it. In Java, can you say where my array starts, where my array ends? No, there is no way. In C, you can. So that gives you a better understanding of how the memory is organized and all that stuff, provided you care. Second thing, this dynamic allocation, okay. Pointers also help you to pass things by reference, get multiple returned values, things like that. The third application is this dynamic memory management. And a fourth application is this, creating a kind of linked structures, which are very useful in computer science, if not in other disciplines too. Yeah. So, any other queries?
Sir, what is this tree-like data structure called?
It's called a tree.
It's called a tree only.
Yeah, it's a tree is called a tree. What else? Anyway, let's not worry about trees. But we will do a little bit about linked lists. Long ago, maybe 15 years ago, something like that, these binary trees were also part of this PDS syllabus, but then students told it's too much, so we just cut down all the trees. We currently have only linked lists.
What is the difference?
Oh, there are two links, so you need actually two pointers.
No, between normal trees and binary trees.
Oh, binary tree means exactly two child. One is called left, other is called right. Okay.
So you have double and like double pointed linked list, like pointing to the next node as well as the previous node.
Here also I can have something like W linked list, something, a pointer pointing back. Okay. Yeah, we will look at these things. But this is not still a tree. This is called a doubly linked list. You can move forward, move backward.
Yes, I was that.
Okay, anyway, in due course of time, we will look at this type of structure. And I would say this is the culmination of our study of pointers. It's very difficult to do this without pointers. And your linked list can grow as long as your memory can permit. And you have severe restrictions if you have static arrays. Okay. So in Java or Python, this kind of dynamic structure is already handled by the compiler. You don't need to worry about, but C is a little bit more primitive language. So you yourself can create your structures, whatever you want.
Sir, in second year, if I'm say in electrical engineering, can we take data structure algorithm courses like from CS?
Well, in one of these, okay, we offer it in both the semesters. One semester is essentially meant for CSE students. The other semester is essentially it's meant for external students. So you apply, and whoever the teacher, but I mean there are too many students who apply. So we have to make a CGPA based screening depending upon whatever we can support. But anyway, I think 150 to 200 students we support everybody every year. Okay, so you can take it.
Okay, sir.
Yeah. Okay, so shall we call it a week?
Thank you, sir.
Okay, bye.
Thank you, sir.
Thank you.
Okay, bye.
Thank you, sir.
Thank you, sir.